So you have already seen till here, that is concentrated load. So today we'll do a problem which is a mixed problem. When you have uniformly varying load and uniformly distributed load, both are there between two points. It is loaded. One is pin joint, another one is roller joint, and you also have concentrated load over here, that is 20 kilonewton, as you can see, and uniformly distributed load of 20 kilonewton per meter. Okay, so this is small w, this is load, and this is uniformly varying load. W per unit length is changing with length. So hope you understood this. These are the spans which are given. Okay, spans are distance between any two load variations. Okay. So now how will you attempt this? First of all, you have to find out the reaction forces which are here and here. So what you will do? You will do your standard approach, that is using free body diagram of the standard beam and taking moment at A is equal to 0. You can take moment at D or B, anything, but preferably I always prefer starting from left to right. So I have taken it at A is equal to 0. So now RB is unknown. RB is reaction force at B. So this is okay. So RB is at a distance 5, 3 plus 2, that is 5, and it is in counterclockwise direction. So that is why I am taking it negative. Okay. And then how did you get this much? Where did I get this? So it is because of this load, this triangle load. Okay. And it says 20 kilonewton per meter at this end. It is 0 kilonewton per meter over here. So it is uniformly varying load. Okay, it is not uniformly distributed. It is distribution is varying. Okay, so because it is triangle, so I have calculated it this much. Hope you have understood this. If not, I'll draw this in a different way now. So let us say this is 60 kilonewton per meter. For somebody who haven't understood, this is 0 kilonewton per meter. Okay. So overall mean variation, if you see a equivalent load of uniformly distributed load, it should be something around 60 plus 0 by 2. Okay, so it should be something like this if it is uniformly distributed load. So it is 60 by 2, that is what may be the first term. And where does it acts on all over this space? So total load what is acting is 60 by 2 into 3. 60 by 2 into 3 is the total load that is acting from here to here. Is it correct? 60 kilonewton, yes. So it is from here to here, if sum them all, so you should be getting almost 60 by 2 into 3 kilonewton, that is the downward acting load. Okay, so that is what is this. And then where is it acting? Where is it acting? It is acting at a 2 by 3 from this, 2 by 3 from this end. Is it not? Because it is 1 by 3 from here. Okay. So 2 by 3 of 3 meters. So that is where it is acting. This is the center of load, where it is equivalent load that is acting. So that is how it is you are getting. So 60 by 2 is the mean load variation, that is uniformly distributed load equivalent, into 3 is the total load that is coming over here, and then 2 by 3 times of 3 is the location where it is acting. Okay, it is the location where it is acting. So overall what you get is 60 by 2 into 2 by 3 into 3 square. So that is how you got. So hope this is quite clear. I won't be explaining this every time I see uniformly varying load. This is the first occurrence and I have explained it. I hope you have got it well. If not, you can come back to this slide and revise it. Okay, now coming to the second part. Second part is quite okay. It is because it is uniformly distributed load of 20 kilonewton per meter acting over 2 plus 2, that is the 4 meter span. So total load that is acting downward is 20 into 4. Okay, and where is it acting? From A you have to measure, it is at the center, it is symmetrically about B. So 2 plus 2, it is 4 total was there. So it is acting over here. So how much it is? 3 plus 2, that is 5. So that is what is this? Okay, so and that is acting downward. Okay, that is acting downward. This is acting downward, and this I assume it is acting upward. The last one, which is a concentrated load of 20 kilonewton, distance where it is acting is 3 plus 2 plus 2, so that is 7. So overall sum of all the moments about A is equal to 0. So I will equate it to 0, and what did I get? Exactly RB. RB I got it as 144 kilonewton. 144 kilonewton. If you solve it, you will get this. This is the only unknown which was there. Now that I already know RB, and that is 144 kilonewton acting upwards. Okay, so sum of all the loads acting downward and upward should equate to 0. Okay, so RA is the unknown which I want to find out. This is known, rest all the loading is already given. So I'll sum them all again. So RB is 144 Newton. Hope you got this also. Hope you got this. Again, triangle load 60 over here 0. So mean loading is 0 plus 60 by 2. Uniformly distributed load into span, that is 3. So it is 60 by 2 into 3. So this is the load, total load acting downward, and 20 into 4 for this uniformly distributed load and 20 kilonewton. Got it? So overall what I get, if I solve this, I get RA is equal to 46 kilonewton. So RA is equal to 46 kilonewton, that is acting upwards. So this too is quite clear. This is using equilibrium of bodies the way we used to do. Okay, so now moving ahead, I'll divide this section again into pieces. How should that section go? Exactly, wherever you see a type of loading ends, you end your section. So this is from here to here 1, from here to here 1, although loading is uniform for the whole span, but because there is some load that is from the downward in between, okay, due to this reaction at B, so I have split it in another half. So C to B another, and B to D will be another one. So total 1, 2 and 3 sections will be there. So starting with the first section, that is AC, and distance going from 0 to 3 meter. If it is distance, it is in meter. I haven't mentioned it. If it is load, it is kilonewton over here. Okay, I have mentioned it here. Okay, so now I'll do what? I'll simply take the any distance which is at a distance x from A and between A and C. Okay, so using again similar triangles, so how much should be y, that is the loading over here, load variation over here. This is 60, this is x. Okay, overall here is 3. Okay, so 3. So using similar triangle, 60 by 3 should be equal to y by x. So y should be equal to 60 by 3 into x. Y should be equal to 60 by 3 into x. Got it? So that is what is y. So I have used that loading over here. Okay, so again shear force, you are taking shear force. So total force acting downward for the section which is at a distance x from here, total load acting downward is, so 60 by 3 into x. So it will be mean into x. Mean 60/3 into x is the variation. 0 to 60/3 into x. 0 to 60/3 into x, it has varied. So if you again equivalent loading, which is uniform, is 60/3 into x by 2 will be equivalent UDL, right? Into x will be your total load that acts in this section. So hope this is clear. If not, I'll come back again. Yes? Very good. So again, moving ahead, next, you just substitute RA which you have extracted here, you have found out here, okay. So this RA you substitute here, what you get is 46 10 x square, and that gives you an equation of a parabola. So shear force between A to C will vary as a parabola as expected. So it is a parabola, okay. So now I'll find out at the extremes, because I have to plot later stage, I have to plot them all. So at x is equal to 0 and at x is equal to 3, at this location and this location, I have found out the values, specific values. So you see it is plus and it is coming negative, okay. So bending moment again, bending moment how I'll do? So bending moment should be, if it is at a distance x and it lies between A and C, so 46 was the upward force that is acting due to reaction at A. So 46 into x is like this. So it is positive because it is trying to make your beam something like this, and this one. So whatever is the load from here to here is tending to make your beam something like this, is it not? So that is the reason it is negative. Now using similar approach, it is 60/3 into x, x by 3 is the place where it is acting, x by 3 is this location. If x is the total distance, x is total, so this should be your x by 3 location where you see the center of this load, okay. So that is why it is x by 3, and 60/3 into x is the variation of load. So using a similar principle, I have found out this, okay. So total load is this, x by 3 is the distance where it is acting, so that is why it is making it like this, okay. And this is the negative sign that goes, okay. Solving this, you got what? 46x into 10 by 3 x cube. This is cubic, as expected it is cubic. Bending moment for uniformly varying load should be cubic. For uniformly distributed load, it is quadratic, it is quadratic. Shear force for uniformly varying load is quadratic, okay. So these should be remembered, okay. For shear force for uniformly distributed load is linear, for uniformly varying load is quadratic, okay. So it goes like that. So this is how AC, till AC was little puzzly because it was uniformly varying load, but later it should be quite easy, okay. So we have done the most difficult part of it now. So again, calculated at the extremes, at A, bending moment at A as expected it should be 0, and at C it is 48, okay. So these two values will help you to draw the plot at the end, okay. So these are there, so this is the load, okay. Now taking section CB, CB is between, X lies between C and B, I am talking about this region, okay. So whenever load due to uniformly varying load will come, it will come as complete, okay. Whole of this load will be taken, and where is it acting? It is at a distance of this, that is 1 meter. It is at 1 meter from this, that is where it should act downward, is it not? 1 by 3 of 3, so that is where it should act, okay. And shear force now, shear force So this is the load 46 kilonewton that was acting upward at A, RA you calculated. So, so 60 plus 0 by 2, that is the uniformly distributed load acting over a distance 3 meters. So that is the total load acting downwards. Hope you got it. Initially it was 0, finally it is 60. Okay, so mean is 0 plus 60 by 2, 0 plus 60 by 2 into 3, that is the distance. So that is the reason it is this. Okay, so this is the total load acting downwards. So you see a negative sign. Now talking about this region. Where is that? Let me clear it off a bit. Okay. Okay. So now which region? It is a distance x that lies between C and B. So in that case, load due to uniformly distributed load. Okay. So how much is that? It is if it is x till here, so x minus 3 is this distance, is it not? So that is where it is acting 20 kilonewton per meter into x minus 3 distance should give you the load which is acting from here to here. Got it? So that is the distance. Okay. So that is acting downwards. So now simplifying that I get 16 minus 20x, and you see it is linear. This is linear. Okay. So that is the load. This is the load at extremes, that is x is equal to 3. I should start from here and I should end till here. Okay. So that 2-meter span peaks were this. Okay. These were the loads. Okay. Now moving ahead, bending moment. Bending moment which is at a distance x from A should be 46 into that distance x, that is straightforward. Now whole of this load is acting. Okay, whole of this load is acting, whole of this triangle is acting. Where is it acting? It is acting at a, hope you got it, just a sec, let me redraw this. Okay, so this is the triangle. How much is the load and where it is acting? It is acting at, this is x, till here it is x, and it is 2 by 3 times of 3. So it is acting at, this is 1 by 3, sorry, this is 1 by 3. Where is your 2 by 3? 2 by 3 is this distance. 2 by 3 times of 3 is place where it is acting. Okay. So x minus 2 by 3 times of 3. So it is the place where it is acting. Okay. So it is exactly that location. And how much is the load that is acting downward? It is mean load variation 60 plus 0 by 2 into total distance, that is 3. So this is the load, this is the load, this is the distance. You got it? If not, I can come back once again. Very good. Yes. So just let me put it down once again. Somebody said that. So this is your triangle. Okay. This is a uniformly varying load. This is 0 and this is 60. So mean load variation is 0 plus 60 by 2. This is an equivalent uniformly varying load. Okay. And this is acting in a span of 3 meters. So I have multiplied it by 3. So this is the total load that acts downward due to this triangular loading condition. Got it? And where it acts? It acts at a distance of 2 by 3 from this distance. It acts over here. And how much was that? That is 3 meter. So it acts at a 2 by 3 into 3 from here. So how much it is from this? If this is x, you subtract 2 by 3 times of 3 to x, you will get distance from here to here. Got it? So it is this distance, okay? It is this distance, okay? So 2 by 3 of 3 was this. This is your x, so this is your exactly this much. Got it? Okay. So now moving ahead, so this immediately can give you, yes, please. Is it? Am I audible? Yes, I am audible. I think I am audible. Just a sec. So you got till this point, right? Till this point, it was quite okay. Yes, yes, I'll do it. Don't worry. Yes, so till here this is okay. So you got till this point. Why it is so? Okay. So now you can mute. I'll continue now. So this is the triangle loading. That is what I explained just now. So it is at a distance of, if it is 2 by 3 times of 3 from this end, so it is from this end that was calculated. And how much is this? This is x minus 2 by 3 times of 3 distance. So this is the distance, this is the load, and that is what is acting downward, and that creates this moment. So this is quite okay. And then remaining part of the beam, okay, remaining part of the beam, how is the loading? That is second part of the loading, that is uniformly distributed load of 20 kilonewton per meter at a distance x, and you have to take only this much of distance. Is it not? So this till here, because you are at a distance x, okay, where you are interested. So it is, if this is x, so from here to here, UDL, uniformly distributed load, is x minus 3 distance, it is there. So 2 by 3, 20 into, sorry, 20 into x minus 3 is the total load that is acting downwards. And where it is acting? It is acting at a distance of x minus 3 by 2 distance, because it is a cuboidal load. So it exactly acts at the center. If this is x minus 3, so it will act as at a distance which is x minus 3 by 2 distance, that is acting downwards, and I am interested at this section, okay. So this is the place where I am interested. So it is 20 into x minus 3 into, this is the load and this is the distance, okay. So that is what gives you bending moment at x. Hope this is quite okay. So effectively, if I simplify this again, I'll get a quadratic equation as expected. It is exactly this, and I have taken values at the extremes, that is at C and at B, because I am in section CB now. So that were the extremes. So these are the values. Now for section BD, that is this section, okay. This time shear force again will be, due to this, you see shear force, whole of that load will come 46, this upward force 46 kilonewton, that is coming. Then this load will also come here also, okay. So that is downward, seen here, and then because it is x, this time is somewhere over here, okay. So this time, you have to take whole of this load which is going downward. So it is 20 into 2, because it is right till B. So it is 20 into 2, and then 144 144 Newton that was acting upward. It is this load that you extracted earlier, and 20 into x minus 5. Why it is x minus 5? This time x was still here, okay, from this end, okay. So, and this is your 3 plus 2, it is 5. So, this is the distance, okay. Apart from rest, which can be considered as a complete thing, this is complete, this was complete, this whole of this is acting upward, this is acting whole upward, only this is the one which is breaking, okay. So, it is 20 into x minus 5, that is the distance which is acting downwards. So, that is the force, shear force that is acting downward, and that is why it is negative. Got it? So, now again I will simplify this, I will get a linear equation as expected. Okay, shear force at extremes, extremes are at B and D, because this time x is in this region, x is in this region. So, these are the two values. Taking back again bending moment, same way, this time x is whole of this distance, 46 into x, x is whole of this distance, x is till here, okay, till here, okay. So, that is there, and you have this triangular loading that you know how to calculate now. It is exactly the same way as we did earlier in this, if you remember, same part will go here also, okay. Another part will again come back, this one will also be there, okay. Only thing that is added now is bending moment due to this load. This was not considered because we were in this region earlier. This time you will take this also, okay. So, if it is x minus 5 will give you this distance. So, this is x minus 5. So, that is the distance, okay. So, 144 into x minus 5 is bending moment due to 144 kilonewton, that is reaction at B at this point, okay. So, that is total bending moment. Simplify that, I got a parabolic equation now. So, that is all. So, now all the sections are done. Now, there is a query, of course, that should be, I have calculated even at this point, I calculated all the way long from here to here and considered all the loads that are due to pieces, due to this, due to this, due to this, due to this. Why not? It can be done directly due to the part which is on the right side of it. Yes, it can be done and you will get similar equation. Okay, assuming now measuring for D, this is an alternative way you can do it, because you see lot of loading which is there on the left half of it, you can directly take, if it is along at this region, it is good to do due to loading which is on the right half of it, okay. So, I have taken it that way alternatively. So, this time A is equal to 7 minus x. What is A? A is the distance, okay. So, it is 3 plus 2 plus 2, that is 7, and this is your x, x is total distance taken from this end. So, this is your A. If this is your A, I have used A to find out the moment at this, shear force at this location, okay. So, we will see how it goes. So, it should be 20 into A, 20 into A. So, because it is 20 into A is the distance, okay. So, that is due to UDL, uniformly distributed load, it is 20 into A, that is the downward load, and a force of 20 kilonewton, that is this one, okay. So, that comes here. So, total shear force is this, shear force at B comes out to be 60, shear force at D comes out to be 20 kilonewton, even using this equation, okay. So, exactly the same as we could do using this section, okay. So, you see it is 60 and 20, it is 60 and 20 using alternative approach also. Similarly, I can do it with bending moment. Bending moment, again you take this point which is at a distance A. A is 7 minus x, remember that, okay. So shear force at A should be equal to 20 into 7 minus x plus 20, you did it already. So shear force should give you this, and it is with varying with A, it can, if you substitute this value instead of A, you get what? It is this. So that is shear force at x. Similarly, bending moment minus 20 into A. Why it is minus? Load is trying to make it something like this, okay, convex upward, so it is negative. So it is 20 into A, that is the bending moment, and then 20, this 20, not this 20. So 20 into A by 2, 20 plus 0 by 2 into A square. So this is exactly that. Okay, so this is acting at a distance A by 2. Okay, 20 into A is the load, 20 into A is the load acting at a distance of A by 2, it gives me 20 A square by 2. So that is the thing. So this is in terms of A, you can get this equation. So you can either substitute A is equal to 7 minus x and calculate in terms of x, or you can substitute directly A. For this A is equal to 0, for this A is equal to whatever. Okay, so that is what it gives me again, 80 kilonewton meter, and bending moment at D should be equal to 0. So both of this arrives at the same value. Both of this will arrive at a same value. Okay. So I would suggest when it is something like this, when you see loading is simple on the right side of it, you can always proceed from the other side. Okay. So even for the section CB, even for the section CB, CB is this section. Because of this, all the problems are arising. Okay, it is not so easy to do. Rather, even in this region, if I would have taken all the loads on the right half of it, so you see just a pointed load which is here and uniformly distributed load which is on the right side of it. So you could have considered, even in this case, you could have considered from the right side, and you will arrive at the same value. Okay. So I hope you got the trick how to solve this on. Okay. So I think, yes, of course, shear force, how was the positive and negative convention which was there? You just remember that, I think you can do it. If you remember your shear force convention, so how was that? Exactly this. You just need to follow this. Okay, and bending moment, you have to follow this. Done. If you can remember these two, you should be happy about it. Okay. So I think with this, almost we are done. I have told you all the things that should be told. There are many. Yes. Where bending moment for the section BD? Yes, bending moment. See what all loading that has come here. I'll just come back once again so that you will remember if it is there or not. Okay, so I'll just come back. So this is 40x due to this focused load. This one, this is due to triangular load. This one, this is due to the uniformly distributed load till here. Got it? And 144, it is due to this load. So nothing is remaining. If you are here, I am taking from this end, this, 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 and this. 4 loads are there, 4 terms are there. Everything is considered, right? Yes. CD, yes, CD. Yes. Yes, 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 please tell me. No, it is not. See, this is 60 kilonewton. This is the varying load. It is not a focused load. It starts from 0 kilonewton per meter to 60 kilonewton per meter. So load variation is not uniform. Okay, load variation is not uniform. In this case, you have to understand, if it is uniformly distributed load, load varies, okay, with 20 kilonewton per meter. So every meter you move, you have 20 kilonewton that goes. But in this case, it is not like that. Okay, it starts from 0 kilonewton per. Yes, point B. Yes, it should not be different. Yes, 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 of course. See, X is different. You are in between, when you are in between CB, X is till here. But when it comes to this section, your X lies between BD. How can it be same? It is not the same. Yes, there is, yes, yes, yes. There will be a sudden change. That is noticeable. That is noticeable. Yes, it is different. Yes, yes. Immediately you will see a sharp rise and fall. Yes, yes. Yes, yes. Both are sharp different. Both are different. Yes. Yes, yes, yes. That is expected. Yes. That will be visible even on the plot. Let me go to the plot so that you can see that clearly. So it is having two values at this location. That is what. So this is your curve. Okay. So this is how it should vary. Starting from this goes to this, and again it matches with this value. Either you take from this section or this section, but in this case it doesn't match. Okay, if you take from this section you get this value, you took from this section you got this value. Yes, there is a sharp change because of the reaction force that was acting over here. Okay, when you are in this section, this reaction force played in. Got it? And that goes and makes it something like this. So the difference should be exactly equal to that. You could see that it was how much? 144 kilonewton. If you remember that reaction at this. So you see 84 and 60. So that difference is there. It is because of this reaction force. So when it is in this section, you saw this value 60 kilonewton, but when it comes from this section, you don't see this reaction force and you see 84 kilonewton. That is the reason. So this is how all the plots will go. So this is the shear force plot, and if you take the bending moment plot, it is something like this. Okay, and this is the point, this is a point which is a very very important point, which is known as point of contraflexure. Okay, why this is important? You see bending moment changes its sign. It goes from positive half to negative sign. Okay, it changes its sign from positive to negative, and this is the place where you can see there is quite high possibility that it may bend or fail. Okay, so that is why this point is of very very interest of for any civil engineers or any engineer who is designing such system. Okay, peaks are important. Peaks are important where you will see the maximum thing. Also the point which is of very very importance is point of contraflexure, when you see the change in direction which is happening. Okay, so it changes from positive to negative at this location. So that is why this point is also sometimes useful, and it is asked to find out what is the value at that particular region, at that particular point, okay, and where does that point lie actually. So in order to find out, you just equate the value of this equation to equal to 0, you should be getting it, okay. Wherever you see 0 in this equation, you substitute it, you will get that value, okay. So I got something around 2.14, this AC, no, this was the maximum using maxima and minima theorem, okay. You use maxima and minima theorem on this and calculate the maximum value where it is acting. You can equate it to 0 to see where is point of contraflexure, okay, and again maxima and minima to see this value, okay. So these are the point of interest, where it is 0, where it is changing the sign, where it is going maximum. So these are the points which are useful and it may be asked, okay. So this is your shear force diagram and this is your bending moment diagram. I think most of the problems will loiter around these things only. Okay, so you got the philosophy of it. Mostly how UDL, UVL can be handled, uniformly distributed and varying loads can be handled. Okay, pointed load, concentrated loads, how they can be handled as well. So you now know almost everything which is there. Now things will be like, you may be given different types of loading at different places, that's all. You will just play with that, that's it, and nothing change you will see, okay. Okay, that's all I think.